All right, ladies and gentlemen. So today what we're going to do is we're going to go through some average atomic mass practice. So if you guys want to open up your Canvas pages and go to the average atomic mass. Yesterday you guys should have learned how to calculate average atomic mass. I just want to go through an example problem together before you guys go off on your own. So there's 8 problems on this worksheet, and so average atomic mass or relative atomic mass. Hopefully you guys remember from yesterday, or you learned yesterday, that it's how we calculate that average mass number at the bottom of the every element symbol on the periodic table. So those average atomic masses are going to be the total mass of all of those isotopes that we have on Earth. So anything that's natural is going to have an average atomic mass of all of its naturally found isotopes. So the example problems that they gave were chlorine. Chlorine had 2 isotopes, chlorine 35 and chlorine 37. And who could tell me what isotope means again? Who remembers what isotopes are? No one remembers isotopes?
Elements that like different neutrons.
Perfect. So they have a different number of neutrons, which also means they have a different mass number. So if we're thinking about these elements, a couple that we can think about that have differences, like chlorine had chlorine 35 and chlorine 37. They also talked about uranium and the fact that uranium had 3 different isotopes. If you guys think in the future, we're going to talk about nuclear chemistry. And so in nuclear chemistry, they talk about uranium, uranium-238 versus uranium-235. One of them is a little bit worse than the other one. Uranium-235 is what they use for nuclear explosions versus uranium-238, which is what they use in nuclear energy factories to get energy from nuclear power. So those isotopes, they do a lot of different things. And so calculating that average atomic mass is going to let us know what the average is when we find all of these different isotopes in nature. So if you guys open up your average atomic or relative atomic mass worksheets for today's assignment, we're going to go through that first practice problem together and then maybe the second one, just to make sure we are all on the same page with what's going on. All right. So this one says that boron has 2 common isotopes. It says calculate the relative atomic mass for boron 10, which has a mass of 10.013 AMU and a percent abundance of 19.91%. And boron 11, which has an average atomic mass or relative atomic mass of 11.0093 AMU and a percent abundance of 80.09%. So a couple things we need to know in this problem. The first one being we have boron 10 and we have boron 11. So we have 2 different isotopes of boron. And it tells us the mass of each one. So this one has a mass of 10.013. And this one has a mass of 11.0093. AMU right here are the units that we're going to use. That is atomic mass units. That's what that stands for. When I say AMU, that's what I'm talking about. So those are the units for the atomic mass. And then that percent abundance. So percent abundance means that if I'm looking in nature, 19.91% of the time I'm going to find boron 10, and 80.09% of the time I'll find boron 11. So if I'm picking up boron off the sidewalk, which probably won't happen, but if I am, I'm picking up most of the time, or 80.9%, 0.09% of the time, I'm picking up that boron 11. So in order to find out the average atomic mass, hopefully yesterday you remember, we are going to take the mass and multiply it by the percent abundance. And when I multiply it by the percent abundance, I do need to convert this into a decimal point. How do I convert that number into a decimal point? Does anybody know?
Multiply it by 100.01.
Perfect. So we're going to divide by 100 and multiply it by 0.01. So if I convert this one, 19.91%, if I want to make that into a decimal, how would I do that? Can you tell me the answer for that first one?
0.1991.
Wonderful. And then if I wanted to do that for my 80.09%, what would I turn that into as a decimal?
0.8009.
Perfect. All right, so now we have two more steps before we finish our problem. The first step being is we are going to multiply these two together, and we're going to multiply these two together. So we're going to take 10.013 and multiply it by 0.1991. Can anybody tell me what you get when you multiply those together?
$1.9935883.
All right, and then we're going to do the same thing for the bottom. So we're going to do 11.0093 times 0.8009. What do we get?
8.81734.837.
All right, so now our last step when we're doing these problems is we're going to take those two values and we are going to add them together.
$10.81093.
Awesome. All right. So now we have to do two last things. The first thing we have to do is make sure we're in the correct number of significant figures. So let's look at our starting values. How many significant figures do we have in here?
5.
5,
What about here?
4,
What about here?
4.
4. And here?
6,
6. So how many significant figures should we use? 4, 5, or 6?
4.
4. Perfect. So we do 10.81. And the last thing we have to do is we have to add those units, those AMUs. We got to add those AMUs right here. And then we have our final answer. Are there any questions on how we did that? Everybody okay with that? I saw a couple of thumbs up. I saw some head shaking. All right, so then just one more thing. Just want to give you guys a hint, and when you're thinking about this, and then I'll let you guys kind of work on your own. I don't expect that you guys need to follow along for all of these. If you want to stay, you can. Otherwise, in just a second, you're good to go. But the hint I want to just make sure you think about is these have to add up to 100% right here. Those percent abundances add up to 100%. If we look, this number right here, our average, remember that the average has to be in between your two values. So it can't be larger than your largest value, can't be smaller than your smallest value. I'm saying that just because I know in the past I've seen it happen where we get a value, let's say we have these two values and all of a sudden we end up with 14. Then we know we've made some sort of mistake if we end up with a 14 because 14 is larger than our largest value. So just make sure your average falls between your smallest and your largest values. If you guys want to do another one, we can. Otherwise, you guys are good to go and work on this worksheet on your own. If you have any questions, just let me know, okay? All right, those of you who are still here, do you guys want to do another one together?
Yeah.
Yeah.
Do we want to do number 2, number 3? We got 8 of them, so your choice.
Can we try number 3?
Number 3, all right. So number 3 says argon consists of 3 isotopes. Calculate the relative mass of argon. So it says the mass number is 36 and its relative abundance is 0.337%. If it has a mass number of 38, its relative abundance is 0.00630%. And if its mass number is 40, its relative abundance is 99.6%. All right. So what I like to do is start off my problem by writing out, I have argon 36, I have argon 38, and I have argon 40. All right, so we're going to start off with that, which means the mass number for argon 36 is that 36. That's why we wrote it up at the top. Just like in a nuclear symbol, that's where your 36 goes. So argon 36 has a mass number of 36. Argon 38 is going to have a mass number of 38. And argon 40 has that mass number of 40. All right. Now for this one, it's a little bit different than the first one in terms of significant figures, because in this one we looked at these. For the rest of them, or for the ones that they don't have this value like this, the 25.938, when it's not perfect, when it's not the exact number that is up here, we're not going to use that as part of our significant figures when we're doing the end of our problem. So for now, we don't have to worry about that, but later on when we talk about significant figures for this one, we're only looking at the significant figures from our percents. So we have our mass numbers, and now we need the percent abundance. And we need to turn that percent abundance into a decimal point. So do you guys know how to turn this one into a decimal point?
Divided by 100?
Divided by 100. So if we do 0.337 divided by 100, what are we going to get?
You'd get 0.00337.
Perfect. What about the second one? 0.00630. If we divide that by 100,
It'd be 0.0000630, or just 63.
no, you're right. That's perfect. Because if we get rid of this zero, it gets rid of that significant figure because that zero counts. So we want to keep it there. And then the last one, 99.6. What do we get when we turn that into a decimal?
9.96.
You said 9.96?
Wait, is it
Or
point
no,
nine
it's
six?
0.09.
There we go. There we go. 0.996. All right. Everybody okay with all that?
Mm-hmm.
All
Yep.
right. So now if I asked you, before we even do any calculations, if I asked you, argon, where do you think the mass number is going to be closest? Do you think it's going to be closest to 36, 38, or 40? What are we thinking? Anybody have any ideas?
Closer to 40.
Probably closer to 40 since 99.6% of its mass or its relative abundance, when we find it out in nature, 99.6% of the time, it has a mass number of 40. So it's probably going to be closest to 40. Now, the last thing we need to do here is we're going to multiply these across to each one, and we're going to solve for those values. So we're going to do 36 times 0.00337. Can we tell me what they get?
Zero 0.1213.
Awesome. All right. The next one, we do 38 times 0.0000630.
0.002394.
All right. And then the last one, 40 times 0.996.
39.84.
Awesome. So now once we have all our values, what are we going to do with them?
Add.
Add them together. Perfect. So let's add these three together. And can anybody tell me what we get?
$39.9636.
All right. And now we just have to check our significant figures. So for this first number, this first percent, how many significant figures are here?
3.
3. Perfect. 3 sig figs. What about the second number? How many significant figures are here?
3 also.
3 significant figures. Perfect. And the last one, how many significant figures are here?
3.
3. Wonderful. So our answer needs how many significant figures?
3.
3. So can anybody tell me in 3 significant figures, what is my answer?
39.9.
39.9. So remember, we look at this one. Is this make it round up, or do we keep it the same?
Round up.
Round up. So instead of 39.9, this is going to round this number. This 9 rounds up to what?
10.
A 10, which means it leaves a 0, and we put a 1 up here, which means that this becomes a, what number?
10 or 0.
A 10
40.
or 0?
40.
40.0. And then our units, AMU.